Okay, let's consider some examples of conservation of momentum. So here we have a very large fish that has a mass that's 4 times the size of the little fish. And the little fish is traveling to the left at a speed of 5 kilometers per hour to start with. The big fish swallows the little fish, and now they move to the left with a speed that is much smaller. So the speed afterwards is 1 kilometer per hour. So where is this all coming from? So first, the big fish has a mass that's 4 times as big as the little fish. So since they're telling us values that are like this is so much bigger than that one, then we'll just go ahead and put some numbers in. So let's just say that the mass of the big fish is 4 kilograms and the mass of the little fish would be 1 kilogram since it's 4 times as big. We also know that the big fish initially is not moving, it's just sitting there. And the little fish is traveling to the left at 5 kilometers per hour. So there's that 5 kilometers per hour, and it's negative because the fish is traveling to the left. After they collide with one another, right, they're both traveling together at exactly the same speed. In other words, this is an elastic collision, a perfectly inelastic collision, because they stick together, so they're both going to have the same final speed afterwards. So if we look at conservation of momentum, we know that the momentum of the system initially, which is the momentum of the big fish plus the momentum of the little fish initially, has to equal the momentum of the big fish plus the little fish afterwards. So we can start to plug in some of our numbers. So the big fish is not moving initially, right? So its initial momentum is going to be 0. The little fish is traveling at negative 5 kilometers per hour and has a mass of 1, so we put that in. And then afterwards, they both have the same speed. So they both have the same velocity, and I can just write it like that, where their mass is in front of their velocities. So the 0 momentum of the big fish cancels out, and so the total initial momentum of the system is negative 5 kilometers per hour, which is fine. We can leave it in kilometers per hour. And this should make sense because the only momentum is to the left, which is our negative sign. And then because both of the fish afterwards have the same velocity, I can factor out that speed because they stick together. And so if I factor that out, I can add their masses together. 4 plus 1, it gives me a 5. So if I divide both sides by 5, I get that the final speed of the system afterwards is 1 kilometer per hour, and the negative sign just means it's traveling to the left. So that's where that animation is coming from, using this idea of conservation of momentum, and this is specifically an example of an inelastic collision where the objects stick together, and when the objects stick together, they're always going to have the same final speed after the collision. So here's another animation that is similar to what we talked about earlier when we started this idea of interacting objects. So we have a frictionless surface, and we have a cannon that has a mass of 100 kilograms and a cannonball that has a mass of 50 kilograms. There's some TNT in there that's causing the explosion and the interaction between those. So there is a force exerted on the cannon, a force exerted on the cannonball. It's equal and opposite, so momentum is conserved. And the system is just sitting there before the explosion, so the initial momentum of the system is 0, which means that the momentum afterwards also has to be 0. So let's think about what's going on. The mass of the cannon is 100 kilograms, which is 20 times the mass of the cannonball. This means that in order for momentum to be conserved so that the total momentum after the collision is 0, the speed of the cannonball is going to have to be 20 times greater than that of the cannon. So let's actually throw some numbers in here and just see how this works. So we know that momentum is conserved. The initial momentum of the system has to equal the final momentum of the system. The A here is going to represent our cannon, and the B is going to represent the cannonball. So initially, the cannon and the cannonball are at rest, so they don't have any initial momentum. Those are both 0. Afterwards, the cannon is going to move to the left, and it has some velocity, so its momentum is the mass 100 times its velocity. and the cannonball is traveling to the right, it has a mass of 5 and it has some velocity associated with it. If I add these two together, they have to equal 0. So what numbers would I have to put in here in order to get these two to add up to 0? Well, first of all, one's going to have to be negative, which makes sense because the cannonball is traveling to the right, it has positive velocity. The cannon is traveling to the left, it's going to have negative velocity. And since these are related to one another by a factor of 20, it's going to make sense that this velocity for the cannon is going to have to be 20 times less than that of the cannonball. It's going to be traveling much slower than the cannonball. Mathematically speaking, what we could do is we could, since this left side of the equation is 0, I can move one of these terms to the other side of the equation. When I move it to the other side of the equation, it becomes negative, or I subtract it from both sides of the equation and it cancels out here. And I get minus 100 kilograms times the velocity of the cannon has to equal essentially the momentum of the cannonball. Now, if I wanted to see how they're related to one another, I can divide both sides by 5, right? And if I divide 5 by 5, I get a 1, and if I divide 100 by 5, I get 20. So this is telling me that the speed of the cannonball after the interaction has to be 20 times the speed of the cannon after the interaction. And the negative sign is just implying that the velocity of the cannon and the cannonball have opposite direction. So those are just a couple of animations that help us see what's going on with conservation of momentum. Let's look at another example, and this is similar to some problems that you could see as you're working on, problems involving collisions in physics. So here I have a 1.5 kilogram cart that's traveling to the right at a speed of 4 meters per second. So that is the blue cart here. It has a mass of 1.5 and it's traveling to the right at 4 meters per second. It collides with a stationary cart, so there's the red cart. That cart has a mass of 1 kilogram and it's stationary, so it does not have any initial velocity and therefore it has no initial momentum. This is the situation before the interaction or before the collision. After the carts collide, the 1.5 kilogram cart, the blue cart, travels to the right with a speed of only 2 meters per second. And we want to determine what is the speed of the 1 kilogram cart after the collision. So as soon as you see collision and you see interaction between objects, there's nothing else involved other than the collision, then we can think about conservation of momentum. So here is our picture before and after the collision. So we can start by determining the momentum of the blue cart initially. And the initial momentum of the blue cart is the mass times its velocity. So 1.5 times 4 is 6 kilogram meters per second. And I can determine the momentum of the red cart. And of course, it's at rest, so its initial momentum is just 0. So before the collision, the total initial momentum of that system is just adding the momentum of the blue cart to the momentum of the red cart. So 6 plus 0 is 6 kilograms meters per second. Now let's see how that compares to the situation after the collision. So after the collision, we know how fast the blue cart is traveling. We can calculate its momentum. Its mass times its velocity. Its mass is 1.5, its velocity is 2. So it has a momentum after the collision of 3. And we could ask, what is the momentum of the red cart after the collision? Well, we don't know what its velocity is, but we know its momentum would have to be its mass times its velocity. Its mass is 1, and its velocity is unknown. So how is this going to help us? Well, we know that this is conservation of momentum. We know that there's nothing from the environment interacting, so it has to be that the total final momentum, which is just the momentum of the two carts after the collision, has to equal the momentum before the collision. So regardless of what we get for each of these right here, the way we've written it, it has to be that when I add these two quantities together for their final momentum, it has to equal what they started with, which is 6. So if I plug those values in, I know that the blue cart had an initial momentum of 3. The red cart, I don't know what its final momentum is because I don't know how fast it's going. But I know that if I add these two quantities together, or these two quantities together, it has to equal 6. And so that means that the final momentum of the red cart has to be 3. So if I use that and I substitute that value of 3 back up in here for the momentum of the red cart, I know that it's going to have, that momentum has to be equal to 3, and that will allow me to figure out what this velocity is. So 1 kilogram times the final velocity of that cart has to be equal to the momentum of that cart, which has to be 3 according to conservation of momentum. If I divide both sides by 1 kilogram, I get that the final speed of this cart has to be 3 meters per second. So this is another way that we could approach problems. We can look at the momentum of each one of these initially, add their values together. That's the total initial momentum of the system. And then I can do the same thing afterwards. And it has to be that if I add their two momentums together afterwards, this quantity and this quantity, it has to be what I started with. Okay, let's consider another question. So in this particular question, I have the same initial conditions that I had before. So I have the blue cart traveling at 4 meters per second, has a mass of 1.5. It collides with a stationary cart, but instead of the carts moving separately after the collision, they're going to stick together. So they've got some sort of Velcro here that's going to cause them to stick together. And I want to know what is the speed of the two-cart system after the collision. So if this is a system that is stuck together, I can think about this as having one big mass associated with it, which is just the addition of the two masses, 1.5 and 1, which is going to give me 2.5, and then that system has some final velocity. So let's see how we can approach that. So just like before, we can figure out what the initial momentum of the system is. So I have cart, the blue cart, its mass times its velocity is 6, just like before. The red cart has 0 initial momentum, just like before. And the total initial momentum is still 6. So the initial conditions for this question did not change compared to the last question. All right, but now let's think about what's happening afterwards. So afterwards, I want to know what is the final momentum of my system. So the final momentum is the mass times the final velocity, where this mass is the total mass of this entire system, which is 2.5 times its final velocity. I don't know what the final velocity is, but what I do know is that momentum is conserved. So the total momentum that I started with, which was 6, has to equal the total final momentum afterwards. So these two carts together have to have a momentum of 6 kilograms meters per second, but that has to equal their mass times their velocity. So I can divide both sides of this expression by 2.5, and I take 6 divided by 2.5, and I get a final speed of 2.4 meters per second. Because they're stuck together, that's the speed of both of the carts after the collision. All right, so one more question, very similar to the last one. Same initial condition here for the blue cart, but now the red cart is actually traveling to the left. So let's see how that affects our answer. So the blue cart initially still has a momentum of mass times velocity of 6 kilograms meters per second, but the red cart is now moving. And so its momentum is no longer 0. So the momentum of the red cart initially is its mass times its velocity. Its velocity is traveling, the object is traveling to the left, which is negative. So 1 kilogram for its mass times a negative 1 meter per second gives me a negative 1 kilogram meter per second. So the total initial momentum of this system is just the total momentum of the blue and the red cart added together, taking into account direction. So if I take 6 and I add to it a negative 1, I get a total initial momentum of 5. So now I have less initial momentum that I'm starting with compared to the previous case. The objects still stick together. I would expect that they're going to be traveling slower because they're not going to have as much momentum. They started with 6 before, now they only have 5, and so they shouldn't be able to travel as fast afterwards. So same thing as before, the total final momentum of this system is the total mass, because they're stuck together, times their velocity. But I know that momentum is conserved, so this final velocity has to equal whatever the initial, not velocity, this final momentum has to equal whatever this initial momentum was. So 2.5 times the final velocity has to equal the final momentum. If I divide both sides by 2.5, there's a typo here. This actually should say 5, not 6. So let's just cover that up. That's 5 divided by 2.5, and I get 2 meters per second. So the carts are traveling slower because they have less final momentum afterwards, which means that they're going to be traveling slower because momentum is mass times velocity. They have the same mass, but they have less momentum after the collision.